So we're going to start out with a brain break if you need it. So using the clues below, fill in the blanks with only consonants to form six common words. All the vowels in these five words are exactly the same. Number one, a donated organ operation. Number two, emphasizing text with color. Number three, fibbing. That's probably the hardest, one of the harder ones. Four, fortress or citadel. Five, tiered track structure. That's where the people are sitting. And number six, conifers. You can pause the video real quick here if you want to try guessing a couple of these before we go on. But if not, here we go in three, two, one. Correct answers were transplant, highlighting, untruthful, that's kind of a strange word, stronghold, grandstand, and evergreen. Today we're moving into the idea of a spring. Springs are interesting. If you think about springs, here's a spring that's unstretched, hanging from the ceiling. Um, if you stretch it, that means you've displaced it in this particular spring, you've displaced it downward. How far did you displace it? Well, if you look at this part right here of the spring, um, we've displaced it from here down to here. So this would be my delta x, my displacement. What direction is the spring exerting a force at this point? Well, it's exerting a force upward. And that's true for every single spring. The force that the spring exerts is always opposite its displacement. And long ago, someone discovered that, if you take a spring and stretch it further, it's going to take more force. And the amount of force is directly proportional to how far you stretch it. That's a really bad drawing. In this case, I'm trying to draw that you stretched it twice as far. It's going to take then twice as much force, or the spring's going to exert twice as much force if you've displaced it twice as far. And likewise, if you displace it 3 times further, it should be 3 times as great. And I'm trying to draw my best here. So double the displacement, double the restoring force. And the first person who came up with that one, his name was Hooke, he got a law named after himself. And this is Hooke's law. The force exerted by a spring is always equal to some constant. We'll talk about this in a second. K is called the spring constant, and it's different for every single spring. Some springs have a large spring constant, they're very stiff. Other springs have a small spring constant, they're very easy to stretch. And then blue here is our displacement. The negative sign here it confuses a lot of students. For the most part, you can ignore the negative sign mathematically. What's the negative sign here for? Well, the fact that both force and force and displacement are vectors, and they always point in the opposite direction. And so the force that a spring exerts is always opposite its displacement. Some springs start out already pre-stretched, like think about the springs in your suspension of your car. If you compress one of those springs by pushing it inward, the force it exerts is going to be opposite. So in this case, I'm pushing it this way to compress it. What direction is the spring exerting a force? Well, now it's going to be downward. Again, always the opposite direction. And that's what this negative sign is in the equation. Does it affect it mathematically? No. It's just that these two vectors are always in opposite directions. If you grab a real spring, you can actually try this. We're going to talk about this a little bit. I'm going to give you some data in just a moment in the Hooke's Law Lab. Take a look at this. So here's a simulation. If you stretch it one way, it requires a force that way. This is the applied force being drawn down here. The force that the spring exerts is going to be opposite. And over here, this is the spring constant for this particular spring. It's represented by K again. And that's just a quick example. So here's a real example real quick on this one. Here is a graph of force versus displacement for a spring. Notice as you stretch it further, greater displacement, the force gets larger and larger. My question is, what's the spring constant? Well, we know the equation is force equals negative K times delta X. And again, remember, we can ignore the negative sign on this one. How do we find K? Well, divide both sides by force, and I'm going to drop the negative sign real quick. Divide both sides by displacement, and we'll get the spring constant. And you might say, oh, that's nice, but how do I get that off of this graph? Well, if you look at this graph, and I'm going to pick one point right here, it's kind of nice, or these 2 points. It looks like this is just about 0 here. And I can actually calculate the slope of this line. And you might say, wait, why is the slope so useful? Well, remember, slope is defined as rise, which in this case is going to be the change in the force measured in newtons, over the run, which I'm going to draw kind of this way, which in this case is the change in the position or the displacement. The slope is rise over run. It's going to be the change in force over the change in position or displacement, which if you look up above is going to be what? Well, it's going to be the spring constant. So if you find the slope of a force versus displacement graph, it'll always give you the spring constant for a particular spring. What is it in this case? Well, in this case, looks like we go up a total of 100 newtons in force, and the displacement here is about 0.5 meters. So what's the spring constant for this particular case? Well, 100 newtons over 0.5 meters, or 200. But what are our units? It's 200 newtons per meter. And that literally means that this spring requires 200 newtons to stretch it 1 meter. And if you look at this graph, yeah, I think you probably see right here, if we continue the graph on, it's right around 200. The spring constant literally tells you how stiff the spring is. The next piece I want to talk about in this one, is elastic potential energy. Elastic potential energy is represented either as EPE, elastic potential energy, or U sub S. U represents potential energy, S for spring, or sometimes U sub E for potential energy elastic. If you stretch a spring some distance x, the force goes up to this. And the question is how much energy is stored in that spring? Well, if you remember back from way back when, work is equal to force times distance. Well, in this case, the force is constantly varying as I increase the distance that I stretch the spring. But the work is actually going to be equal to the area of this triangle. And you're like, oh, wait a second. What's the area of a triangle going to be? Well, it's 1/2 base times height. In this case, that would be 1/2 times x. And the height, how much force does the spring exert if it's stretched a distance of x? Well, using Hooke's law, that should be kx. And so if you multiply that through, and you can already see it in the notes over here on the left, 1/2 x times kx gives us 1/2 kx squared. And this is the formula for the energy stored in a stretched or compressed spring or rubber band, where x is how far you stretched it, and you got to square it, and k is the spring constant for that particular spring or rubber band. The units again for this are joules, the same as all the other forms of energy. Sorry, just quick doing that one. And I want to quickly talk about your worksheet for tonight, 0402. In particular, I want to do questions 3 and 4. The rest of it, I think you'll be able to figure out on your own. So on this force versus displacement graph, we have two springs being drawn on it. Uh, Spring number 1 is data set 1, drawn with the little square points. And data set 2 is spring number 2, drawn with the little triangles. Question 3 is determine the spring constant. Well, if you remember again, the spring constant is just going to be the slope of this graph. And since both of these start out at 0, it makes it pretty easy if we can find a nice point. And for data set 1, I'm going to use, whoops, that didn't end up very good at all. I'm going to use, I'm just going to draw it, I guess. I'm going to use this point right, let's see here. I'm going to use this point right here. That point seems to be at 20 newtons, and it looks like it's almost exactly at 4 meters. Now, I think my graphics are going to be bad on this one, so just ignore it. Just look at that point. Yeah, that is really off. Actually, I'm using this one here, but I'm not sure why my graph is off so badly. This point here is at 10 newtons. All right, that works out fine. So force is 10, displacement's 2. And what's the spring constant then for this first spring? Well, it's 5 newtons per meter, just 10 divided by 2. And for my second one, again, my triangle's off for some reason. I'm going to use this point right here. And that seems to line up with 16. Ignore my graphics again because they seem to be off. And that's also at 2 meters. So 16 newtons at 2 meters, the slope is going to be 8. For question 4a, determine the amount of force required to stretch the spring 3 meters. To do that, I'm going to just use Hooke's law again. And for the first spring, the force spring constant is 5. We just got that from up here. And we're stretching it 3 meters from here. So how much force is required? 15 newtons. And I'm going to drop the negative sign again. Just look at the magnitude. For spring number 2, doing the same trick, the spring constant for the second spring is 8. And we're stretching it 3 meters again. So it's going to require 24 newtons. Finally, what's the elastic potential energy stored in each spring when it's stretched 3 meters? We're going to use the elastic potential energy equation we came up on our last slide, 1/2 kx squared. For the first spring, plugging in our numbers, the spring constant again is 5 for the first spring. And we're stretching it 3 meters. And if you solve this, 5 times 3 squared, 9, is 45, times 1/2 gives us 22.5 joules. And for the second one, very similar process, except now the spring constant is 8 from here. Stretching at 3 meters gives us 36 joules. The rest of the worksheet, when you work together tonight, you should be able to sort of figure this part out. But I at least want to get you started on it. Your lab is Hooke's law, and you'll see a link to it from here. And we're going to look at the spring constants for 2 springs. One's a short one, one's a longer one. The apparatus is shown over to the side there. You can look at the lab sheet. It's linked to your assignment sheet. Except just to make things easier and to make sure that things go all right today, I'm going to give you the data. And you'll find that link to it as well. So here's the data we're going to take. Here's the short spring, here's the long spring. And one of our goals is to create graphs of force versus displacement for each spring in Excel. Make sure you label the graph, and then add a trend line to each graph, rewrite it with the appropriate variables and units, and what are the spring constants for each spring. So the data, you'll see actually, so here's the lab with all its questions. You'll have to open that. But instead of actually doing the lab, I'm going to give you the data, which is right here. And then finally, I'm going to have you, there's another video linked here which talks you through how to actually graph it in online Excel, find the trend line, and rewriting it, all the things that I'm asking for. And I'm doing it for one spring, and then you should be able to use that same procedure to do the other one. The data I'm going to give you is this. The data here is actually from another group that did this lab. Their data is not perfect, but it'll be enough data to actually be able to have you graph these two and find their spring constants. With that, you should be all set. Good luck with this. Um, Work with each other to help write up the lab and work on the worksheet, but you should be in good shape. Good luck. Talk to you soon.